In this unit, we're looking at exponential functions. Anything in the form y equals a times b raised to the x power would be an exponential function. We typically think of these in two categories. We're looking at like growth and decay, typically here. And the difference then between those is our b value. If it's growth, then our b value is greater than 1. And if it's decay, then our b value is less than 1, actually between 0 and 1 for that decay value. Now the other thing we would look at is if we have a negative exponent, well, we could write it as a positive exponent and take the reciprocal of that b value. That's then typical to a decay type problem. So any of your exponent properties we'll want to make sure we're using as we work through these types of problems. Now we might also see something in the form y equals that same a value. That's typically your starting point on these, and we might have something of 1 plus r. R would maybe be like your rate or your percentage of increase or decrease raised to the x. This would be similar to a formula that we would also find for compound interest. If we're looking at a compound interest formula, something that could be compounded, say monthly or weekly or whatever it might be. Again, we would have a as like our starting amount that we have in there, and then we are adding whatever rate interest we have. And if it's being compounded, say monthly or weekly, that n value is how often something is being compounded. And then we would have our n times t as far as our exponent goes, where again that n is our compounded, how often, and then t is our time. So for example, let's say that we have a rate of 6% that we're earning as interest. We're going to invest $400. And let's say that it is compounded monthly for 3 years. So then as far as finding out what that total amount would be when we're setting this up, we're starting off with $400. And then we have our rate of 6%. And so we'd write that as a decimal. That's going to be 0.06. Because we're compounding it monthly, then we divide by 12. And so that means we're going to take 12 times 3 to find out how many times that we would compound that. And as far as that amount, this is where we can use our handy dandy graphing calculator. And I can plug the whole thing in at once. I have 400 times our 1 plus 0.06 divided by 12. And then we're raising that to the 12 times 3 power. So that would give us a grand total of $478.67 after those 3 years. Now there's lots of other places where we can look at things being compounded or some sort of exponential growth and decay, as long as we're talking about compound interest. What if something is compounded continuously? We've already talked about, and this is review from previous classes, that if you're compounding continuously, we have a different formula for that. Anything where you're talking about continuous change involves the number e. It's got its own special button on the calculator, and for compound interest type problems we have our formula PERT, where we could use this same example that we just did where we took our $400 and now our rate's still 6%, our time is 3 years, only now we're going to say it's compounded continuously. So if we take our 400 times e raised to that 0.06 times 3, again, we have the button on a calculator that is e raised to the whatever power you have. So in this case, we have a rate of 6% times our time of 3 years. And so compounded continuously, and again, this is only over 3 years, but that compounded continuously adds it up to $478.89. Now, other ways where we'll see exponential growth and decay, carbon. Carbon-11 decays. Make a new problem here. Decays at 3.5% per minute. And so when we're looking at that, as far as thinking about our formula, whatever amount you begin with, we have this plus R. Well, if it's decaying, then we would think of it as a minus R. And so when you're looking at setting up a problem here, we could say that, well, we're starting at 100%, and then I have a decay rate of 0.035 raised to the x. So what we end up with is 96.5% of whatever we started with after each minute. This subtracts to 0.965 raised to the x. Now, as far as solving these, anytime if we're looking at maybe trying to find the half-life of something, then we're going to say that I want to find out, well, when is there half of that amount remaining? And so, we're saying that we start off with 100%, so when I have 50%, that's our half. So it's 1/2 is equal to the 0.965 raised to the x. That would be the half-life, is how long is it until I only have half of what is remaining. And when we do that, anytime we're solving an exponential function where our variable is an exponent, that's when we use logarithms. And we'll do more with logarithmic functions in the next section. But for this example, anytime I'm solving for that x, I'm going to rewrite this as a log. And so what that means is I'm going to take this, here's my base. The base is the base, so in this case it's 0.965. So I have log of 0.965 is my base. Log base 0.965 of 1/2 is x. And so this is the part that we can use our calculator for to solve that logarithm, or to solve for x. Our exponent is where our variable is. Remember, our calculators are set up to be base 10. So we would use change of base on this. What means I'm going to plug into the calculator log 1/2 divided by log of the 0.965 to find out that x value. So we have log of 1/2 divided by the log of 0.965. So that means the half-life of that carbon-11 would be 19.456. And that's minutes. So it doesn't stick around for very long. Remember, as far as graphing exponential functions, if I'm looking at something like y equals 2 to the x, this is an example of exponential growth. Like you're folding paper and it doubles every time you fold it in half the number of sections. So for example, you start off with one piece of paper, so 0 folds in 1, you fold it in half once, and now you have 2 sections, folded in half twice, now you have 4. Remember, anything to the 0 power is always equal to 1. So in all exponential, whether it's growth or decay, all exponential graphs will go through the point 0,1 unless we are multiplying this by some other number. But just in general, we'll go through that point 0,1. Now, if it is growth, now it's going to be going up. So then I'm at 1, 2, and I'm at 2, 4 when I plot these points. And remember, we also have an asymptote. and our asymptote is with the x-axis because it doesn't make a difference as that x is approaching negative infinity. It doesn't matter what value I plug in for x, this will never reach 0. So that means that that line is going to go forever and ever along the x-axis but never intersect it. So where that line y equals 0, that would be our horizontal asymptote for this exponential growth function. Now when we're looking at exponential decay, now the only difference is now I'm saying that I have half as much and it's decaying each time. Again, that 0.01 is still part of this graph, only now it's getting smaller each time. So now I have half as much there and half as much there. When I'm on the negative side, then I had more to begin with, and then at -2 I was at -4 up here. And so now we can see that it's coming down here, and now it is going to again go along that x-axis forever and will never intersect. That is still our horizontal asymptote where y is equal to 0. Solving exponential equations, we need to pay attention to what our exponent properties are as well. Now remember, we can use a one-to-one property, in which case I'm going to really try and focus on the base to begin with and having the same base. For example, 2 could be written, or we have 2 here, I could write 4 in terms of 2. It's 2 squared. So this one doesn't change. The 4 I'm going to change to 2 squared, and I still have the 2x as my exponent there. I could also write the 8 as a base of 2. That would be 2 cubed. That's my rewriting of the 8, and I still have the 3 minus x here. Now our properties for exponents tell us that we're going to multiply these. I would also multiply this quantity, 3 minus x, by this exponent, so we're going to have to distribute that. Now remember, once we have the same base, now we're looking at those exponents and solving that way. And because we were multiplying here, that means we would add these. So I have my exponent of 2 plus, here when I multiply that I get 4x is equal to, and I'm distributing here, so I have 9 minus 3x. Because we had the same base, now we're looking at just the exponents and solving for there. Now we just solve this. I'm going to get the variable on the same side. Here's my equal sign. I add the 3x over to here. I'm going to subtract this 2 over to this side. So 9 minus 2 is 7. Divide both sides by 7, and we find that x equals 1. We can always then go back and plug that 1 into our original and check our answer.